who is here, a great graduate student who's looking for a postdoc position now, and also Aneth Kandala, who is at the University of Florida, another really great graduate student, and Ben, who just talked, and Shabib Amin, who is also wonderful and really grateful to have such talented graduate students right now, and a collaborator, Joey Paulson at Syracuse, and also a great collaborator, Allison Pattison at Syracuse. And I guess there is a couple of, right? I should have practiced. Yeah. Mouse pad is not quite working. In
the middle.
In the middle, the space bar maybe? Okay, good. I'll just use space bar. Okay, and so we want to again focus a lot of the lead authorship is Videhesh, and the work done is presented in 4 papers here. Well, 2 are accepted, and the bottom 2 are preprints. So if you're interested, you can certainly check out the preprints or come talk to. Actually, all of us are here, meaning Anna, Viv, Videhesh, and Ben. So we all have our reasons for being here. As we discussed yesterday, and we've certainly seen the photograph of the board that I cannot create, I do not understand, from Feynman. I would maybe modify that slightly. What I cannot train, I do not understand. And so my main reason for being here is using learning in physical systems, both dead and living, to gain new insights into them, not necessarily to build a faster learner, a computer per se. And by living systems, one could be a brain organoid. Here is a brain organoid from the study of Watanabe and et al. And I also want to just give a shout out. I just realized this morning that I have another brain organoid paper that is now submitted addressing if you have a brain organoid that is your control type and you have a brain organoid that's genetically mutated to capture the essence, if you will, of lissencephaly, or the genetic mutation that helps drive lissencephaly, which is the smooth brain. There are actually mechanical differences between those 2 types of organoids, which is kind of interesting. And in walks also phsyarum is another living system that I've been inspired by, particularly due to Karen Alim's work, who is here now. And so I guess Logan had the quote, the software is the hardware. I guess I sort of have a similar thing. The material is the brain paradigm. And so we want to ask the question, what kind of emergent properties can arise? Right. So inspired by the brain and phsyarum, where different types of physics exists, such as electrical networks, mechanical networks, chemical networks, all in the same system. We have phsyarum that has mechanical and chemical signaling. We have the brain, which has electrical. We've seen many of the models discuss the Hodgkins-Huxley, the McCullough-Pitts, I don't know if anyone mentioned Wilson-Cowan, all sorts of equations that basically capture a neuron as a circuit. But they're also, as we know, neurotransmitters in the brain. And interestingly, when you build electrical network on the right, this picture here, there are chemicals that basically communicate from one neuron to the other. So there actually is chemistry going on as well in the brain. So if we can answer this question in the supervised learning case, perhaps we can get some hints about the unsupervised learning case, which is where I'd like to go, and maybe that'll become clear in a moment. So given this inspiration that in biology, you have different types of physical mechanisms going on at the same time, or different parts of the network, whatnot, let's sort of set up a simple system that Benjamin has studied, and the group of Andrea Liu and many others have studied, these resistive networks that also the math is applicable to phsyarum, and maybe actually we could call it a flow network too. The same math is involved. So we will say here voltages, but maybe then, in the end, we'll go to pressures. And there are many ways to train, as we've been seeing in terms of all these different algorithms, the equilibrium propagation, coupled learning. These, of course, are contrastive learning paradigms, as we've discussed, or has been discussed. So given that there are many ways to train, let's propose a few constraints. And Benjamin hinted at this in his talk a few moments ago. Of course, we want to have local learning rules and local external internal local external inputs and outputs. Thanks. And the learning dynamics should approximate gradient descent. And based on this contrastive learning idea where we need two copies of the system, let's see if we can get around that by, again, invoking this multi-mechanism or having different physical mechanisms involved in the learning. And so as we go for that, the basic idea behind multi-mechanism learning is you have an input signal that propagates into the system via physics. That's our state variables, our fast physical variables. It's some physical observable, it's activation signal. And then we use a different physical observable for the feedback signal. But in this case, it's going to follow the same physical mechanism. It doesn't necessarily have to. It just makes the math a little bit easier in this case. So you could have principal two different physical mechanisms, the activation and the feedback. And so again, the idea is that the multiple physical observables can exist in the system at the same time. So here's your schematic. Okay. So now if we think of a setup of a network, we have our adjustable weights. As we know, we have nodes known as X and Y are hidden nodes. They're not connected to any inputs or outputs. We've got, for various reasons of simplification, we have input node pairs. So we can have a current flowing into one input node and flowing out of another input node pair. And this causes, of course, we go now to the flow network and resistor network, flow network, same math, at least for now. There's a pressure drop that, or pressure that develops at every node X in terms of these internal or hidden nodes. Here, of course, just for fun, here's a, for Videhash, we know how to, given our physics 101, as Benjamin mentioned, our Kirchhoff's loop rule and the conservation of current rule, we can figure out in the current's inputs, we can figure out what the voltages or pressures are in this case. And then we can, of course, figure out the pressure drop across the edges. And it should match the desired, but it may not necessarily. Of course, how do we do this? This is achieved by this cost function, but trying to minimize the cost function. As we know, I'm going fast because this is, if everyone is. And interestingly, there's this nice update rule. What we then do is, after sending the activation signal and finding out pressure drops, we find, aha, the pressure drops are not necessarily the desired ones. So what we do is we're going to feed back in, say, a chemical signal by fixing some chemical feedback currents, epsilon I and minus epsilon I, and those, the magnitude or the amount of the feedback current will depend on this big C is the cost function, will depend on the cost function in this way. And so after we then find the chemical concentrations at each X node, which we now denote by U, we now have another field, if you will, that's generated in this feedback field. Then we can update all the weights by using a product of the activation field, if you will, and the input, feedback field. Okay. And so in this case, again, both resistor or flow networks are governed by the Laplacian matrix for now, linear networks, nice and easy. Though we're very tempted to, that Benjamin has this more sophisticated nonlinear simulations, hopefully up and running and being made public soon. We'll do some simulations with some nonlinear networks. And we can use two different chemicals or types of currents or physical mechanisms for two different chemicals. If you want to think of a chemical analogy in the flow, we can also, which I'll mention, you can also think of if we want to think of resistor networks, we can think of having the input as a DC current. We can think of the feedback as an AC current. So as long as we have two different V's and U's, the activation field and the feedback field, as long as they're two different modalities are distinguishable from each other, we can then enforce or perform, for better or for worse, multi-mechanism learning two M's and one L, so not machine learning. So, but maybe you guys can think of a better name or help us think of a better name. Again, we have the activation signal. Here are input currents. Here's our Laplacian. We have our feedback signal. Here is our, again, Laplacian. Here's our activation, our feedback field, and then we change the weights accordingly. And now you could say, well, Jen, okay, so come up with this. How does it work? Well, does it work? And then, of course, as Andrea pointed out, maybe the IRIS data set is not necessarily the first place computer scientists would start. They might sort of smile but and poke fun, but we're going to start with this anyway. So we have the famed IRIS data set, at least within the context of the physical learning. So here is our initial state of our network, where we have our input pairs and our output pairs in different colors. Here is our final state after doing the performing the algorithm, and you notice that some changes in weights are positive, some changes in weights are negative, up and down. And then, of course, here's now always, as always, the error is a function of epoch or a function of time. We see, yes, it seems to work. Here is the accuracy as a function of time. Okay, about 93-ish, I think, percent accuracy. Not great, but linear network, not horrible. So, not too shabby. Okay. So as I mentioned, frequency propagation is another implementation of multi-mechanism learning. Again, where we do not need two copies. So now what we do is let's oscillate in time the feedback boundary currents. So here is our aimed sinusoidal wave function. And so this leads to an oscillating feedback signal now. There's an assumption here that the system's relaxation time is much less than the time period of the oscillation of this oscillatory feedback current. And so why would we do this? Well, now the signal is seen at each weight of the network is given by the activation field and now the feedback field. But the feedback field now has this modulatory sign factor. And so if we can then distinguish the AC and DC parts, then we're golden in the sense that we've got our multi-mechanism learning working, these two distinguishable signals, if you will. You can do that by your Fourier analysis. So you can calculate the Fourier coefficients for each of the fields and then find the U's and the V's and update accordingly. Okay, so this is now, theta instead of W, okay, with the weights. And here is, again, we've got our network, initial and final, where the coloring is just sort of the change in the weights from their initial values. And again, here we have the error as a function of epoch. And we have the training. We can see the error is decreasing with time. We have here the accuracy as a function of epoch. Again, the accuracy is increasing as a function of time, as it should. Okay, so you can apply frequency propagation to the nonlinear networks. As Benjamin noted, there's beautiful work by Millar in 1951 doing analysis of nonlinear resistor networks, which we don't talk about in Physics 101. But you can use some of the math that Benjamin developed for equilibrium propagation in nonlinear networks and use it to make some mathematical statements about frequency propagation, which again is implementation of multi-mechanism learning. Okay, so in terms of a summary, we have an activation and a feedback signals, and they're distinguishable physical observables. In this case, they follow the similar physical laws, meaning Laplacian governs both, but you don't necessarily have to have that per se. The signals can be used to send gradient information via a local. Maybe I should emphasize that the update rule is local, and it eliminates the need of storing information in multiple phases in terms of the free and the clamp. So that's a nice advantage. And then there's another algorithm also circumvents that just came out recently that Martin gave a wonderful talk on, circumventing the needing for two copies that involves some non-equilibrium memory element in terms of updating the dynamics at the synapses. So you can certainly, I encourage you to look at that as well. So one thing to note, so we should say that the multi-mechanism learning works because one is performing gradient descent in the cost function landscape. Interestingly, yes, the physical variables evolve quickly, while the learning variables, if this is in the language of Andrea speak, one of my heroes, then one could say there's a separation of time scales in the sense of physical system, and bam, quick, but the weights, the evolution of that is on a slower time scale. And interestingly, there's a hierarchy of time scales in biology too, where certain systems date, if you will, more slowly than others. And I think Rebecca Schulman mentioned a little bit that hierarchy of timescales in biology in terms of gene expression versus neurons firing. So let's just now ask, is there any emergent phenomenon in the structure changing this landscape of the weights, this learning landscape, again, in the language of Andrea speak? So if we now train and do another task, many different tasks. Let's do linear regression. So one can generate a random matrices. That's your idealized data set. And you can then train on that. So can your system recognize these input-output functions, or the function that governs the input-output relation. And so here is basically using the multi-mechanism learning, the first version, so not the frequency prop version. And here you have initial and final, and here again you have the error as a function of epoch. So now let's look at the eigenvalues of the Laplacian as the weights are modified. And so here is the eigenvalue magnitude as a function of eigenvalue index, and blue is the initial state of the network. So here, and then after training and testing, here is the red is the final eigenvalues, at least the lower eigenvalues here. And you can see there's a decrease in the eigenvalues as the network learns. Okay, and so here's just a quick sanity check if you use it on random data. Of course, there's no drop in error, and you don't see that same drop in eigenvalues in the spectrum. So a similar emergent softening was observed by Stern, Liu, and Balasubrahmanian, reported in arXiv in 2023, and also by Olmec and Hexner in a wonderful view of physical review research article. And you can also compare this with directed aging. It was headed by Needy, who's coming to Syracuse, where there the weights, if you were guided to decrease. Here we don't do that. We just sort of the system naturally softens. Interestingly, if you fit the error curve to a stretched exponential form, you could try different forms. We saw the other day from Hexner a power law form. If you try to fit the error as a function of time or epoch in computer science speak, this beta governs the stretched versus compressed. And you can see as you change what we call a tuning parameter, which is the number of edges in the graph, compared to the number of edges in the fully connected graph. So you have more and more edges as you go to the right. These graphs, all of these x-axes are TP. Then you have, here is the y-axis is the saturation value here, the beta and the lambda. You can see here that interestingly, as you increase this tuning parameter, you go from beta being close to 0 to being, oops, this should be 1 here, not 0. So you should go from stretched to compressed. Thanks. Right? And so we have a stretched exponential relaxation, which is observed in electronic and molecular glasses. So that's sort of interesting to note. So the learning landscape here is a glassy one. Right? And so in just a few minutes remaining, moving towards unsupervised learning where the weights are adjusted by some physical process. That's where we'd like to go. We don't have to go in by hand and change this, have this update rule. We don't have to do it by hand. We're working towards with Joey and Paulson, working towards a granular learner where as you drive it above jamming, you can think of this coupled hysteron picture Joey and Nathan Keim really developed, and really trying to control, have weights to those hysterons so we can train the hysterons to do something they won't naturally necessarily do. That's one thing. Also looking to train brain organoids, embedded spheroids, and any other oids with in terms of using either multi-mechanism learning or some other algorithm to see what emergent learning roles occur. And this is with Ellie Pattison. And then interestingly, there's a paper which I was a little bit surprised one brought up, but there's this paper that came out last month in terms of brain organoid reservoir computing. Here's a picture from the paper. It's really quite beautiful. Here's the schematic. You have your brain organoid and you hooked up to inputs and outputs. The inputs are some electrical stimulation. The outputs are some recording, recording the output activity of the brain organoid. And then you have some linear regression here in terms of instead of, I guess, your output layer that has the adjustable weights. You have unsupervised learning, the brain organoid is doing its own rewiring. And actually, if you inhibit the neuronal plasticity, the learning is not as good. So quite interesting. And so we have this new concept now, or many people are thinking about organoid intelligence. Okay, so working on that as well. So I think I will just, cell nuclei, I will just end here in the sense of saying that in terms of biology, it's a very multi-scale structure. And so actually you have learning machines, if you will, going on at the nuclear scale. You have learning machines at the cellular scale, learning machines at the multicellular scale. And so we really need to embed, if we want to understand biology, embed that sort of thing, multi-scale structure of biology into learning. And so these two paths I've been taking are now emerging. So I just want to thank you.
Thank you. That was a great talk. Just looking at your networks that you've trained here, it kind of looks like you start out, you start with a very coordinated, highly coordinated network, and then it undergoes sort of a dimensional reduction as it's training. Can you learn anything about that final structure, from that final structure about the problem that you're trying to solve?
No, it works. All right. Yeah, that's a great question. So if you look at this pointer, and this is, I think, a question that's a burning question that's on people's mind. You start off with these weights, you have some initialization of some distribution of weights. And then as you rightly see, some of those weights go essentially close to zero, some regularizer and whatnot. But yeah, a lot of the weights sort of seem to not matter. And Sam noticed this experimentally with his apparatus as well, was pointed out. So really trying to figure out why some weights are going to zero, and you can actually plot the distribution in this. We have plot the distribution and how it's sort of narrowing and whatnot. That's a beautiful question, and one that I'm trying to work toward the answer to. So as I think about it, I will update you. You update me as you think about it. Thank you. Yes, Arvin.
Related question. It's not clear to me if any of these are properties of the learning process, or just like, for example, if you've done the same thing with a genetic algorithm or any other optimization, do we expect the same property of the eigenvalue?
Yeah, that's a great question. And that's one where to think about at least this broad concept of multi-mechanism learning and to try different sort of implementations of it really needs to be done. Right now, we've been very narrow. We only have so much person power, but that's a beautiful question.
Okay, so you did a really nice job at the beginning of talking about what are some of the things that you want in the learning world. And that's something that I told you in giving your background is that you wanted to approximate gradient descent. Is that really necessary?
I don't think necessarily. Okay. I think definitely for starting out with the simple case and understanding that, and the hope was, so working with Benjamin, that maybe some math could be applied and we could have some proofs. So we have a little bit of that, though there's a technical hiccup we discovered. But so I think having some grounding in a simple system, if you will, a simple approach, that is useful, at least in my mind, that's useful. But it's certainly not the end point. So I agree. Biology probably has thought up of, because biology knows more physics than we do, or cells, that there are other ways to basically not necessarily use gradient descent. So I think that's an excellent question. That's something that I say, looking at these brain organoids, trying to train them to do various things. The initial result was training the brain organoid to learn how to play the game Pong. That was a year ago. Now we have this, not me, but this, Dr. Guo and company, where they've taught the brain organoids it can do speech recognition. There are a few tasks in that paper I pointed out. So I think really trying to uncover the learning rules that biology uses is important. And then the question is, if we can uncover that learning rule, maybe it doesn't approximate gradient descent. Maybe it's just some other math that we don't even know yet. So it's beautiful. Yeah.
Yes. In this example, the ratio of edges to nodes is roughly 10. And in the
you know, the breadboard, durian loop, the loop example, it's like 4 to 2. So, but at the end, it seems like the ratio goes down. And the reason I'm asking this is, or saying this is, if I'm trying to build physical versions, if I'm trying to build physical networks that, physical systems that train themselves out of cells or, resistor networks or whatever, it's much harder to start with so many edges. And so is there an advantage to starting with more edges? Is it easier to train?
Well, I mean, yeah, certainly the more edges you have in principle, the easier it is to train. But I mean, you saw the example of Sam and Doug and Andrea and White and any other people involved, and Naki. So yeah, so so that's one advantage, is have more edges. Obviously, it's more powerful, right? So, but the question then could be, and many people have asked in this room, so is there a transition? And I think Professor Hexner pointed that out too, that there's a transition between sort of under-parameterized and over-parameterized and whatnot. So you want to understand where that transition is so that you can then more optimally use your computer or learner.
If I wanted to implement your approach, could I do it with a simpler system physically?
I think so. Yeah. I mean, that's a good point, Tommy, that we should have, what's the simplest, what are the simplest rules, what's the simplest network topology, right? I mean, the fewest amount of ingredients. That's right. Yeah. To be honest, or maybe Videsh is here. Maybe Videsh can also add to that, what's the smallest network we tried here.
Okay, let's thank Jen again. All back here at 10.